Hello and welcome to this video. In this video we're going to talk about fundamental particles and how we know they're fundamental, or why we think they're fundamental currently with our knowledge that we have. So fundamental means that it's not made up of anything else. Okay, so fundamental just means it's the smallest we can possibly make it. Okay, so not made up by anything other than itself. Okay, and for a long time, other than itself. And for a long time, we believed that atoms were fundamental particles. We thought they were the smallest things that could possibly be, and we couldn't break them apart and find anything else inside them. It was just the atom. But we know that atoms can break apart into protons, neutrons, and electrons. And so atoms are not fundamental particles. And then for a while after that, we thought, okay, now we found the fundamental particles. Protons, neutrons, and electrons are definitely the smallest things that we can have, and there can't be anything smaller, until we split the proton and split the neutron, and we found that protons are actually made up, protons and neutrons are actually made up of things called quarks. Okay, and now, whereas electrons are not made up of quarks, we can't split an electron with the technology we have right now. Little disclaimer, most of particle physics is trying to prove that we can split the electron and we can split quarks because of a property called spin that doesn't really make sense to a lot of people. Basically no one understands it. So we're trying to currently come up with explanations for that, but as far as we're currently fully aware, we can see quarks and we can see electrons. Okay, but electrons aren't the only one of their type. So the protons and neutrons are made up of quarks, and an electron is what we call a lepton. Okay, and quarks and leptons are the two types of fundamental particles that we have that make up matter. Okay, there are other types of particles that are there that don't make up matter, but for what we're going to look at today in this video, we're going to be looking at what is a quark and what is a lepton, and why do we think these are fundamental things, and then even why would people argue that they're not fundamental. Okay, so let's first take a look at quarks. Okay, so quarks make up protons and neutrons, okay, but there are different what we call flavors of quark. Okay, so quarks are quite weird things. Okay, quarks have flavor. Doesn't mean people have tasted them, it just means they have different types, and so we call them flavors just as an analogy. There are 6 different flavors. Okay, so we have 6 flavors, and those flavors are, we have an up quark, we have a down quark, we have a strange quark, we have a charm quark, we have a top quark, and we have a bottom quark. Okay, so these are the list of the 6 flavors of quarks that we have. For the A-level spec, we only actually have to worry about these top 3. We won't have to worry about charm, top, and bottom, but it's good to know that they exist, because we'll find that there are also 6 types of lepton, and so there's kind of a beauty in the symmetry that we have 6 quarks and 6 leptons. But for now, we only have to worry about the idea of having up, down, and strange quarks, because all of the particles that we're going to look at A-level are made up of up, down, and strange, and none of them will involve any charm, top, or bottom stuff. Okay, there is a table in your formula sheet that tells you the properties of these up, down, and strange quarks. And they tell you, the thing that I'm going to look at first is just the charge, or this is actually actually no, we'll keep it as charge because we're going to write it in terms of the charge of an electron. So I'm just going to put a little star up here. When I write E, this is the same as saying 1.6 times 10 to the minus 19 coulombs. Okay, so that's just the charge of an electron. Okay, so an up quark you'll find has plus 2/3 the charge of an electron. A down quark has minus 1/3 the charge of an electron, and a strange quark also has minus 1/3 the charge of an electron, which is quite weird, as in why are they thirds? Why can't we just have, or it's, well, kind of weird, but also kind of nice that they're exact fractions of these. We don't have weird fractions. They're quite simple, nice fractions. And this is because of a higher level thing. So this stuff you don't have to know, but it's just interesting. So you can never find a quark by itself. Okay, it's never been seen that you can just see an up quark or you can just see a down quark. They have to form what we call colorless systems. So if you want to look into colorless systems, you have to look at color charge, which gets really confusing. So for now, we're just going to say we have to have things that come together. We can never have a single quark or single like up quark or down quark or strange quark or even top bottom or charm. Okay, and this is kind of nice. So this means that we have to form things. So quarks form what we call baryons and mesons. Okay, so these are the two types of things that quarks can come together to form. And baryons we are already familiar with. We know some examples of baryons. A baryon, so let's make a little table here. Baryons just mean we have 3 quarks combined. Okay, mesons are a little bit weirder. Mesons are a quark and an anti-quark. Okay, we'll take a look at what antiparticles are and what they, how they're different from regular particles in a different video. Baryons contain 3 quarks. Examples of baryons are protons and neutrons. Okay, so protons and neutrons. A proton, this is something you'll have to know. So protons have what we call a quark composition of up, up, down. So if we split apart a proton, what we see is 2 up quarks and 1 down quark. A neutron has 1 up quark and 2 down quarks. Okay, this kind of stuff you can memorize, but you can also figure it out from this table that you're given of the charges. So if I get rid of these charm top and bottom, and let me just prove to you that this is true just using these charges. So if we know protons overall have a charge of plus 1, where 1 is the charge of an electron, so we have just plus E essentially, right? So if we take an up quark, that has a charge of plus 2/3 E. We have a second up quark, so we'll add the charges together, plus 2/3 E, and then we have a down quark minus 1/3 E. So these all have the common denominator, so we can just add them together. So 2 plus 2 becomes 4, minus 1 becomes 3, and 3 divided by 3 is 1. So this is equal to just positive the charge of an electron, which is the charge of a proton. Now we can do the same with neutrons. If we have an up quark, so we have plus 2/3 charge of an electron, minus 1/3 the charge of an electron, minus 1/3 the charge of an electron. For the 2 down quarks, this comes out to be 0, because we have plus 2/3, get rid of one of those thirds, and then get rid of the last third, we have 0 charge left over. So baryons are just 3 quarks combined, and the 2 examples that you have to know are protons and neutrons. Now some of you may already know this already, but if you're unfamiliar, these are never going to change. These are basically the definition of what a proton and neutron are. Okay, mesons are when we have a quark and an anti-quark pair. Anti-quarks, basically, what antimatter is, so this is a little bit of a side note just to introduce to the idea of antimatter. I'll probably do another video going through it in more detail, but antimatter is essentially for every particle that you have an antiparticle. So for example, you can have a proton, but you can also have an antiproton that has all of the same properties of the proton, but opposite. So for example, it will have the exact same mass as a proton, it will have the but opposite charge. So it will have 1.67 times 10 to the minus 27 kilograms, but its charge will be minus 1.6 times 10 to the minus 19 coulombs. Okay, so we can have that same thing. We can have electrons, and we have a fancy name for anti-electrons. We call them positrons, and that's just because we found out about positrons before we found out about antiparticles. So we thought we'd got a brand new particle, and then we just found out that all particles do this, and so they're just called antiparticles. But this happens with all particles, right? So if we have an antiproton, it means we can have anti-up, anti-down, anti-strange, okay? That's what I mean by this Q with a little bar on top. This Q bar is just an anti-quark, okay? Whenever you see that bar on top, it just means it's an antiparticle. Okay, so let's say for mesons, the two that you're going to have to know are called kaons and pions. Okay, and we can usually simplify all of these things down to a symbol. So we'll say protons are just P, we say neutrons are lowercase n, we say kaons are just K, and pions are just pi. Okay. However, mesons are a little bit more difficult, where these ones will always have the same thing. Mesons can change depending on what the overall charge of the meson is. And so let's take a look at these kaons and pions separately. So let's look at pions first. So pions, we can have, so if I come down here, I'm going to just move it up a little bit so we can still see the data. So pions, we can have a pi plus, we could have pi minus, and we can have pi naught. Okay. Now pions are made up and down quarks, just like protons and neutrons. Okay. But one of them is obviously going to be an anti-up or an anti-down. And so you can work out the charges of these things, and working out the charges of them means you can know the quark composition of them. So let's take a pi plus, right? So if we have something with a positive charge, we know we're going to have to get something, so we can add these up to be plus 3/3. Okay, so we already know we want an up quark in there. Okay, so we're going to have an up quark that has plus 2/3 the charge of an electron. Now this is a regular quark, which means the second thing we need is an anti-quark. And the anti-quark, if you remember, has the same mass but opposite charge. It also has the opposite of all the quantum values that we're going to take a look at in another video. So if we have just ups and downs, then down has to be anti-down, which makes it plus 1/3 the charge of an electron, and then 2/3 the charge of electron plus 1/3 the charge of electron is just the charge of electron, positive. Okay, and so the quark composition of a pi plus is just up, anti-down. Okay, pi minus is essentially just the opposite, because we'll have a minus 2/3 minus 1/3. So pi minus becomes anti-up, down. Pi naught, a little bit strange. Okay, so pi naught, we need an overall neutral charge, which means we could have an up, anti-up, so they cancel each other out, or we can have a down, anti-down. Either of these is completely okay. Okay, so these are the two compositions that you can have of a pi naught. But there are certain things at play that are a lot more complicated. And for those of you who are interested, this is the idea of superposition. So the way a pi naught actually exists is in a superposition between these two states. So you'll have the pion constantly changing between being an up anti-up and a down anti-down, and so there's a change of quark identity going on at all times. That's a little bit more information than you have to know, but just so you're familiar with why there are two, it's because these are both stable, both unstable, and so it will constantly switch between the two, and it'll never be just one or the other. Okay, so this is pions. Kaons get a little bit even weirder. Okay, so if I scroll down a little bit, I'm going to lose this information, but hopefully we should be okay with that. So kaons are what we call strange particles. Now there's something about the strange quark that does some strange things. Kaons, the idea of having them being strange particles means they contain a strange quark. But what that does, the way we can notice that it's different to having other things, is they have an unusually long half-life. Okay, unusually long half-life, meaning that they can survive for much longer than is expected for something of their energy. So most things will have a half-life that's that we can predict from knowing the energy of the thing, but kaons don't follow the prediction because of the strange particle. Okay, and so we have to kind of alter our calculation and our prediction just to satisfy the strange particle, which is why it was originally labeled as being strange. Okay, these kaons, just like the pions, can be formed as a K plus, a K minus, and a K naught, and they essentially follow the exact same thing, except all of these downs are now strange quarks, because if you remember, the strange quark also has a charge of -1/3 the charge of the electron. Okay, and so does the down quark, and so they're basically the same, but the strange particle has weird properties. So a K plus is going to be up anti-strange, a K minus is going to be anti-up strange, and a K naught is going to be either up anti-up, actually it's going to be down anti-strange, or strange anti-down. Okay, would be the more accurate way that this is going to be found. Okay, so these K plus and K minus follow the same trend as this. The K naught also follows the same trend, except we've now got down anti-strange because these have the same charge, and this is slightly more stable, because if we had up anti-up, it would be a pi plus, a pi naught, not a K naught. Okay, so we have to have the strange quark in there somewhere that makes it a kaon. Okay, and this will be in a superposition between these two states, and it constantly flips back and forth between them. And the last thing I want to cover in this, because of these strange particles, we have a new value that we have to take into account, and that's called strangeness. Okay, so this is another one of the columns that you'll find in this data table in your booklet. So if I just rewrite that out over here, so we'll have the quarks are up, down, strange, and we have their charges, which is plus 2/3 charge of an electron, minus 1/3 the charge of an electron, minus 1/3 charge of electron. We'll also have what we call baryon number here, which we'll talk about in the video on quantum values, but they're all 1/3. Okay, this isn't just for these three. If you went to any top bottom charm, they would all also have 1/3, and you'll see why when we look at baryons in more detail. But then they also have strangeness. Okay, is the last column, and an up quark isn't a strange quark, so it has a strangeness of 0. down quark isn't strange, but a strange quark has a strangeness of -1. Okay, it's just another example of just like charge is a property, or density is a property of something, or the mass is a property, the baryon number is a property of something, and the strangeness is a property of something. Now, the strangeness is going to come in useful because they will tell you in this K0, if they ever ask for the quark composition of it, they will tell you that the strangeness is either -1 or +1. Okay, because that's going to separate these two. Because if we have a regular quark, it has a -1 strangeness. So in here, in this one, the strangeness is -1. But this is an anti-strange, which means all of the values except the mass flip. So we'd have a +1/3 charge, we'd have -1/3 as a baryon number, and we'd have +1 as the strangeness. So in this case, it's +1. So that just allows you to see the difference between these two compositions and how we can identify them using these what we call quantum values that we're going to look at in another video. So this is quarks. Hopefully this will make sense. We're going to have another look at more about them when we do the summary video. But hopefully this all helps as part of an introduction to the topic. Thanks for watching.